some problems from chapter 20, which is kind of where we're at right now in the official sense. There should be some time left at the end of class today to sort of introduce the material, at least to sort of begin a discussion about the material that we'll finish next week. That's material that we're going to sort of talk about at the end of class today. That's in chapter 21. It looks at one particular violation of the conditions when you're analyzing group data, the independence of groups condition. We'll sort of work on that a little bit more next week. You'll have some time to sort of absorb it, so there's no particular hurry with it. I'll introduce it through an example, I think, later today. And you'll see that example again next week, and you'll be able to work on that a bit yourself. So that's kind of where we're at. A few administrative announcements as usual. Remember this week that I guess it's the reading assignment 20 is due. That's over chapter 20. People had some questions about it yesterday, so hopefully we answered those. And you'll be able to kind of make some progress on reading assignment 20 and turn it in. Let's do it the normal day and time. So just make sure that you do your best to get that done by Friday at 5 p.m. There's a homework which is due on Monday, and then a written assignment which is due on Tuesday. I know on Monday I had thought about sort of creating another homework assignment to add onto the homework assignment that you're already doing. I think I'm probably not going to do that. So I'll probably give some optional assignment out there if you really want to work on, computing or doing inference for differences of means or proportions. But we've done quite a bit of that in class anyway. And the written assignment and the reading assignment also sort of help with that. So, I don't know that I need to add very much to what you're doing toward the end of the course anyway. So I think we'll just stick with it as it sits. Next week, I guess that's week 13, if I'm counting right. There will be one last reading assignment to cover chapter 21. There'll be no written assignment, which is assigned next week. So there'll be a total of 8 written assignments, the last one of which will be due this Tuesday at 5 p.m. There'll be one more homework on my stat lab, which I will release probably toward over the weekend or toward Monday. That will be due the following Monday in week 14. And in a sense, that represents sort of the last sort of assignment that you're going to be doing along the way prior to the final exam. So you're kind of almost done with the course. If you've done all these things, you've kept up, you've done a good job. And you only have one more thing to do at that point after that last assignment is complete. I think it's homework assignment 12. You'll have to take the final, and the final will take place in week 15. Final exam will be a lot like the exams that you have taken so far. In fact, I think it's weighted equally with those exams. So it's not really weighted. It's not weighted significantly more. I don't think even at all, if I remember the syllabus correctly. With the other 2 exams, I will release it on Monday morning. I think it's April 26th, and it will be due. I need to go back and consult the schedule, but I think I set it up to be due when the in-person, so to speak, final for this course was scheduled, which is I think on Wednesday the 29th. So you have 3 days to do it this time rather than 5. I kind of have to do that because university regulations are such that I have to turn in final course grades for the course within 3 days of when the final exam is scheduled to end. And so I want to be able to kind of get that done in an orderly way. And of course, if there are any kind of technical problems, I want to be able to adjust to those that week as well. You'll have some ability to take the final at different points in time during that week. So I guess with all that said, does anyone have any questions they'd like to ask right now? Anything of an administrative nature that they want to know about? Is it all okay? Yes, Amira.
Hi, sorry, I might have missed this, but is the final exam just covering the stuff that from the second exam on, or is it like the entirety of the course?
So it will be cumulative. It's the entirety of the course. I'm going to kind of want to keep, I want to keep the length of it kind of under control though. So that sounds sort of intimidating if it's for the entire course, but I'm not gonna create a final that's like 3 times as long as a standard test. So I think the exams were only running maybe, excuse me, sorry, somewhere between 10 and 15 questions. I imagine the final will probably also be 15 questions, but they'll sort of be more loosely distributed. I have to limit myself to things that I think are important so that we don't get bogged down with minutia on the final. So there's 21 chapters, but I'll probably really only ask maybe 15 or 16 questions. So you should probably expect an exam, which is of a length equal to the second exam, but it has slightly broader coverage. So does that make sense?
Yes, thank you.
Yes, Lily.
So I have a couple questions. So one, will we have access to our previous exams and homework assignments? Because when I was studying for the second exam, I was trying to pull up previous homework assignments and it did not let me look at them.
Okay, that's weird.
Yeah, so I don't know if it's happening for other people, but being able to look at those exams and those homework assignments would be immensely helpful. And then second part of the question is, I know I kind of mentioned this a couple weeks ago, but just about how once you answer a question, you can't go back and check your answers. Will that be changing this time
I guess
around?
if people wanted to change. So there are a couple of there are a couple of things that I want to make sure on the final that remain the same. I don't want there to be a time limit on the final. So I don't want to impose like a 2 or 2.5 hour time limit for the test, even though I think that's mostly what people take. I need to look at the options to see what's actually available. One advantage of the don't go back is that it's clearly the case that you don't necessarily need to have a time limit under those conditions. But there's another option I can choose. I just need to figure out whether or not that's compatible with the no time limit feature. I mean, to me, the no time limit is the piece that's significant. I just want people to be able to sit around and work on things for a while. And if there
Yeah,
are,
for
so
me,
I mean, pardon?
yeah, for me, I don't know if other people feel the same way, but yeah, just with the last exam, it was very frustrating because I like one question out of 15 is a huge percentage. So if you hit the wrong one, you're kind of screwed. So that was kind of an issue for me for that exam.
Yeah, so I can. So I don't have an issue with changing that particular piece. I just need to see what the other option looks like for the testing conditions that you're in. Like I said, the the important thing to me, as the person giving the test, is that there's no time limit. But I'll look at it and I'll give you an update. So it's not a big
Thank you.
it won't be a big mystery going into it. I think Jeffrey also had a question or a comment.
Yeah, I was about to ask just about the time limit, but you basically answered my question.
Yeah, I want that aspect to be uniform with the other 2 tests. I don't see a reason to change it. So we'll go ahead and go with it. And I guess that's it. So I guess with the final, if you're sort of following the conversation, if you're if you feel like you're doing well on the exams, you understand what's going on in the course. In my experience, excuse me, I don't know what's wrong today with my cough. In my experience, I don't think that, people, there's really nothing I can put on the final that's that surprising. And we can talk a bit more about the details of it next week if people are comfortable doing that. I want to have a day or 2 in there next week. Wait, next week? The week after next. Week 14, I guess. I'm a week ahead of myself. Where people have the opportunity to ask questions, and maybe we can think a little bit about what might make a reasonable question for the final. So just bear in mind it's out there. It's not going to happen next week, but it's probably about 2.5, 3 weeks away. I need to go back and consult the schedule to try to remind myself of the dates that the final exam will take place. So I guess with all of that in mind, I feel like we're doing very well in the course. The pace has been one where, you know, we're going to cover all the required material in plenty of time. You know, so we can even slow things down a bit. I think starting toward the end of next week, we can cover additional material. You know, that's a possibility. You know, we can go back and cover old material if people feel like doing that, or we can just devote some days in week 14 to simply doing problems if people find that to be an attractive option. So maybe think about how, as a group, maybe you can discuss how you feel like using that last week. I'm open to various different possibilities because I feel like we're, other than canceling the class, which I'm not open to, but it seems like we've done, at least at the end of next week, we'll have done everything that we've needed to do that's officially listed. So what we do the following week could be defined by student interests, could be defined by the sort of things you want to see for that week. So you can have some side conversations about that and let me know what you think. So with that in mind, I think today we'll try to wrap up the discussion of inference for independent groups. And we'll get into a discussion about what happens when the groups are not independent, basically by sort of looking at a particular example of the failure of independent group condition. I think that we probably talked enough about the theory behind the inference. We've written down a bunch of formulas. There's some idea about how to run a statistical test or compute a confidence interval associated to some sort of problem that you formulate, you know, using some sort of pair of statistical hypotheses. We've seen this. I'd like to give groups a chance to work on some things, and I'd like to sort of, you know, maybe give you a few minutes to consider how you might do certain problems. I've got a few in mind. Then I'd like to come back and meet as a group and kind of work through them thoroughly to kind of see where we're at. So to that end, so I'll share the screen. To that end, what I'd like everyone to do, you know, in the next minute or so, is to bring up the text for the course. So, you know, I'll probably draw, you know, some problems from the text. The first problem that I'd like the groups to work on is this question 31. This question involves, well, I'll leave it to you to decide what it involves, but I'll divide people up into groups. You can use StatCrunch to use the summary information right here to come up with the inference. But that's the first question. This is in the book. So you're going to need to open my stat lab and go to page 638 of the text. It's question 31, where I think we will begin in groups. And then after you get a chance to consider this question for a few minutes, I'd like to meet as a class and sort of go through the mechanics of the problem, take a look at what the conclusions ought to be. So let me divide people into groups. Should need, say, 6 today. Remember, it's question 31 on page 638. That's where we'll start. It's about 1:09 right now. Assuming that people will take a little time to bring up the text and work on things, let the groups take maybe about 10 minutes to try to, maybe 12 minutes to make some progress on the problem. And then we'll meet again and kind of work through the problem itself. At this pace, I think we'll probably finish 2 or 3 problems of this sort. I'd like to get one problem where you're looking at difference of proportions, one problem again where you're looking at difference of means, you know, just to kind of cover our bases today. And I think there'll probably be a few minutes at the end of class to introduce the topics that we're going to sort of finish discussing next week. So right now I'm going to open the rooms. About 1:10 now. Let's meet again at 1:20 as a large group, and we will finish this problem 31 from the text on page 638. Groups we're at, we'll see where they're at when they think about this question. So to review the question, I'll bring it up on screen. It's this question 31. We can sort of treat these pieces one at a time, starting with part A. Let me go ahead and write down at least question 31, page 638. So when we're thinking about this type of question, we might ask, in fact, the question is asking, Is this an experiment or was this an experiment? Or an observational study? So we'll write this down, but I'll sort of put this to the group. What do you think? What do you think? What do you think it actually was on the basis of how the problem is stated? Do you think you're looking at an experiment or an observational study? Yes, Lily.
I think we're looking at an observational study because you're not really controlling any variables.
Okay.
And there's not really like random selection, like random distribution into the groups.
Okay, maybe. Abby.
I was honestly thinking the exact opposite. I was thinking that this is an experiment because it talks about how the men were randomly assigned to either undergo surgery or not. So I took that as like the variables were being, I guess, manipulated.
Manipulated, yeah.
Yeah, so that was kind of my idea.
Yeah. So yeah. So if I had to make a decision about it, whether or not this thing was an experiment or not, wait, let me go back to the actual phrase, the actual question, so we can see it. Recently, the New England Journal of Medicine published some results. Men diagnosed with prostate cancer were randomly assigned to undergo either surgery or not. Of the 347 men who, you have the various features of the experiment, which I guess are described here. But I guess what I would say about this is that I would say that it's actually an experiment because you do have different treatment groups, and there appear to be two levels. I mean, you're not told much about the nature of the surgery, I guess. There are only two choices, either no surgery or surgery. Now, if you pause to think about this, it's kind of an odd experiment, right? How would you actually implement it? You can ask, maybe it's not such a great experiment, but you can ask questions about it, like, which might not have anything to do with the randomization, but you can ask about, like, how was this blinded? If you're in an experiment and you're randomly assigned to one of two groups, one who gets surgery and one doesn't, you're probably going to know this. And so, the most naive way is if you make the random assignment and then you either get surgery or you don't get surgery, but the groups or the people that are assigned to the treatments actually know this. So if you do things that way, how do you actually account for the fact that, people, how do you account for the fact that people know that they're not getting surgery? So you do kind of have a treatment, you do have some manipulation of a variable, but it's kind of an odd manipulation, right? It's either surgery or not surgery. It's a very strange sort of experiment. You have to wonder a little bit about the ethical implications of running such a thing. Who actually would have approved such an experiment? Would there be, potential legal ramifications if you are in the group who performs less well? But on the other hand, maybe the people who were participants were recruited and were kind of well aware of the potential risks. So difficult to say what the actual ethical implications are, but it does seem like you are manipulating something, and that's sort of appearing right here. There's some randomization. So, that's hard to say. So, you can imagine trying to blind the experiment by like giving people anesthesia and like trying to convince them that they had surgery or something. But again, that would be weird. I mean, I've heard of cases like that actually where, but I can't remember, the details where people were convinced that they had some medical treatment, but actually they were in the no treatment group. And, it's strange. I mean, the world of running experiments or medical experimentation like this on people seems like it's very perilous from the point of view of the ethics. But in any case, you have some randomness. So it seems like if you're thinking about whether or not do the techniques that we've discussed apply, I mean, it seems like the randomization condition, if the randomization is done correctly, is okay. It's usually the first condition that's sort of you're worried about. Other conditions like the 10% condition, certainly it seems like the groups are far short, far less than 10% of the population of men who get prostate cancer. And I guess I'll leave it to you to check the success failure condition. Remember, I mean, I guess we're talking about proportions here. Either you get or you do not get prostate cancer, so it makes sense to think about that. So it seems like these are more or less satisfied. When you're dealing with experiments, you're probably in kind of a good position. It's not, what's being described is probably not something like a randomized clinical trial, which might give you some pause, but at least it's plausible that these conditions are satisfied based on the description of what you see. I need to write a little bit more down here, I think. If you go back to the problem, I guess in 31, I'd like to treat this in a couple of different ways using techniques that we're kind of familiar with by this point in time. Create a 95% confidence interval for the difference in rates of death for the two groups of men. So in this case, we're counting a death as a success, which is sort of strange. So I need to sort of denote you know, what it is I'm talking about. So for the population, we want to make inferences about things like population. So P sub surgery, let P sub S represent the proportion of men in population of men who die of prostate cancer. So after the population of men with prostate cancer who die of that particular illness who get surgery. So we don't know what this is, of course. We do have an estimate of it, and let P sub no surgery represent something similar for the population of men with prostate cancer, but fall into the no surgery population. And so, you know, you have the two populations, and we're trying to just say, we're trying to infer something. In this case, we're trying to come up with a confidence interval. We're trying to infer something about P sub S minus P sub NS. So it's a difference of proportions that we're actually looking at in this problem, and you know that's what we're regarding as a rate. So before I go on, does anyone have anything? I think there's one thing I didn't mention, but does anyone have any questions up to this point? We sort of labeled everything. We feel like the conditions are mostly satisfied. I guess we should probably think about whether or not the groups are independent, but it seems like they should be. Knowing something about the no surgery versus surgery group, knowing some characteristics of the no surgery group will probably not tell you too much about the surgery group, and vice versa. So in a case like this, we feel okay about the techniques. We're trying to look at the difference in proportions for some two different populations, for two independent populations. And that's kind of where we're at right now. So before I go on and look at the inference, does anyone have anything any concerns, anything you'd like to worry about on this problem? Or is it okay? Okay. So we have some information about an estimate. So we have a oops, we have a point estimate for that difference. And that is the difference of sample proportions, which we represent with symbols that look like this, the hat notation. And in this example, we'll have to write down what these are, but when we write that down, I'll write it down really quickly, but we have a point. So, so you have 347 men in the random sample who had in the surgery group, and 16 died. So I think we would regard that proportion as being 16 over 347 minus the no surgery, and that's 348, that's its total size, and the number of people who died there was 31. So notice that the size of the two groups is about equal. So you're led to believe in this type of work, this type of experiment, you have 347 plus 348 total participants. So, you may have some large number of people who volunteered, and then you get this difference of proportions. And so this is our point estimate. We're out to come up with an interval estimate, which we can of course do very quickly with StatCrunch at, let's say, the 95% level of confidence, and we want to interpret the result when we do that. I guess I should always remind you, what the formulas are. Remember that in general, that's page 3. No, okay. So, we're looking at our estimate, which we know is a number, minus a margin of error, and that whatever that is, that's known as the lower confidence limit. And then we have an estimate plus a margin of error, and the margin of error derives from some estimate of the standard deviation of the sampling distribution of the difference in sample proportions together with the confidence level. So we're thinking about the margin of error in this case being equal to whatever our critical number is times standard error of PS hat minus P no surgery hat. And so, we can write formulas down for all of these things. Might be worthwhile to do it. If it's a 95% level of confidence, then we kind of already know that Z star is 1.96. The value of the standard error, so I'll write it down in the sense of formula, and you can kind of work out what it is on the basis of what we've written down so far if you want. It would be PS hat, so it's whatever that number is, times 1 minus PS hat, divided by the sample associated with the surgery, which sample size, I believe, is 347. And, for the other element in the standard error, you get PNS hat times 1 minus PNS hat divided by the sample size associated to no surgery, which I think was 348, and you get some number. And that's basically how you come up with the interval. So if you were left to your own devices, you could easily come up with a confidence interval. You take a few minutes. You can work it out with a calculator. Of course, you can do it much more quickly than that because we can always go to StatCrunch and use it to come up with the estimate. So let's do that very quickly. So I'll go to StatCrunch. What am I really looking at? I'm looking at the difference of proportions. So I go to proportion stats to sample with summary. Sample 1, we're regarding sample 1 as deriving from the population of men with prostate cancer who got surgery. Success is death in this case from prostate cancer. So that's 16 over 347. With sample 2, from memory, the number of people who died in that group with prostate cancer is 31 out of 348. I hope those are right. I think they are, but we'll see in a second. StatCrunch, you have the option of either running a hypothesis test, which is not quite what we want to do here, or you can come up with a 95% confidence interval, which maybe is what we want to do here. We compute and we get the upper and lower limits automatically. Notice in this case, we get a lower limit, let's say, of about negative 0.08 and an upper limit that looks like negative 0.005. So let's write that down. In this case, notice that both numbers are negative. I'll call it negative 0.080 to be consistent. Write it out to 3 significant digits. So when you're looking at a confidence interval like that, and this is related to the last bit of that question, what does it mean? I mean, there's one observation that I think that's worthwhile here. It's that this confidence interval is negative. So remember that we're saying that the interval negative 0.080, negative 0.005 is a plausible collection of values for PS minus P and S. If this collection of values, this plausible interval of numbers is all negative, then we have some evidence that the surgery, whatever that might be, is effective. And the reasoning is that if that range of values is negative, that means that the rate associated to P sub S is estimated to be lower than the rate with no surgery. So people tend to do better. So it's not that surprising, possibly, because if you look at the point estimate itself, the sample difference is negative 0.04. But in this case, I think that the standard error is relatively, small, so you never really get above 0. So before I go on, does anyone have any questions about what I just wrote? Like, the interpretation is that you're thinking the surgery is actually effective because the confidence interval that we came up with in the context of how we formulated the question is all in the negative side. So, you can approach problems, trying to measure some kind of effectiveness of a treatment in this way. Now, notice that it doesn't look like a statistical test in the same way that you might have looked at something in chapter 18, I guess it was. So you can always ask yourself, what do you think the appropriate formulation of the statistical hypotheses are if you wanted to look into this? You could always do a 2-sided test, and that kind of corresponds to what we just did. You could also do a 1-sided test with the level of significance being 0.025, and you would get a result which is, I think, analogous to what we just got. Now we can do that really quickly if you want, because StatCrunch will naturally do the statistical test, whatever level of significance that you want. But before I go on, do you understand the point of the problem? Like, the reason why you want to know what this estimate actually is you're trying to make an evaluation of the treatment. Do you think it matters that people get surgery? I guess, the counterfactual here is how would you have felt if the confidence interval contained 0? This one does not, but if the confidence interval contained 0, you would feel like you would not have evidence that things, at least at the 95% level of confidence, that you would not have evidence that things that the surgery made a difference. If that makes sense. The fact that it doesn't contain 0, I think, is the important part of the analysis. So before we move on, does anyone have anything to ask, anything to add? So is it all right? So I'll talk a little bit more. The important part, the confidence interval stuff, or even the statistical test stuff. The truth of the matter is that people, you see the formulas in the book, and you feel like it's important maybe to try to remember them. But the truth is that anyone can run a statistical test or come up with a confidence interval using software. I think it's the last point that's important. Why do you care about coming up with a confidence interval, and what does it mean when you do? So in a case like this, trying to evaluate the effectiveness of a particular medical treatment might be of interest. And so trying to come up with a confidence interval for a difference in how groups react, that might be something important to take away from the class. One additional note, and I'll write this down. This type of problem suggests a question which we might get into next week. There's another question that we'll look at today. There's an additional question which is suggested. What happens, what happens if, an experiment or something like that involves more than one, or rather more than two, levels. How do you handle that, right? You can't quite do it in the same way because there's no good sense of, sort of doing more than just pairwise subtraction, if that makes sense. So something minus something else has limited utility. So you wonder how this type of approach, what do we look at? To compare more than two groups. So I guess I'll write it this way: more than two independent groups. We may have some time to talk about that, but an answer to this is, sometimes people answer this in the following way. We try to use something like what we're going to come to call one way.
Sorry, Professor. There was a fire alarm, and I just got back.
Oh, okay.
And
Yeah.
so I assume a bunch of other people just got back as well.
Oh, okay. Well, yeah. So if that's true, I am making a recording. So if you have questions, you'll be able to review that in the event that you were on campus and got pushed out of the door.
Oh, thank you.
Yeah. So the one-way ANOVA is something that might fall into some bonus material that we might have time to discuss, but it really depends on what students' tastes look like when we finally get to that week 14. I feel like I'll leave that part up to you. So with this in mind, I feel like we've talked about this problem. We've done it enough. Yep, got it, Meredith. Yes, and we can maybe try another problem also in groups. So what I'd like people to do is, again, we'll sort of mess with the book a lot today. So let's go to the next question that I kind of have in mind. Looks like it's this question 72 on page 644. So the question that I have in mind is this one right here. It's sort of a description about about mortality rates as related to water. So this is giving you a little bit about some kind of mortality in different regions as related to some measurement that you're trying to make about water. So on a question like 72, so you just have a summary. I'd like the groups to consider it. So again, we'll break into groups. People can work on things a little bit. You're not really dealing with quite the same thing that we were dealing with before. What I would say in question 72 is that you should think a little bit about the distribution in the samples. You have to think about the conditions that permit the techniques that we're talking about to be used. We'll address that ourselves. But let's try that one now. It's about 146. So this is not about proportions anymore. It's about the other technique that we had. And so maybe the groups can try that if that makes sense. So right now about 147,
Sorry, which problem?
Let me bring it back. 72 on page 644.
Got it.
So it's this one right here, hard water by region. You have the summary of the content. So you know the mean, the counts, the standard deviation. So you have to think a little bit about, think about so you're trying to run a statistical test here that might be appropriate. So you're gonna have to think about what might be appropriate here, run the test, and then think a little bit about whether or not the conditions apply, right? Maybe even do that first before you run the test. The question is asking about a particular outlier and the effect that this might have. It's worth thinking about that as well. But that's the question I think that's worth considering next. So let me break. Groups are already ready to go, I think. So I'm about to open the rooms. It's about 1:48. Let's do the same thing we did before. Let's take maybe 10, maybe 12 minutes as groups to consider it. Let's meet again at about 1:58 or so as a large group, and we'll sort of finish up with this question. Room should be open. All right. So welcome back. So I'd like to try to finish up with this question, think about it a bit, raise some objections, maybe to the techniques we're going to use, but then use them anyway. So when we're thinking about this problem, let me bring it back. It gives you a description of some previous problem. You may not have looked at that problem, and that's probably okay. So what's being reported here is some kind of death rate per 100,000 in 61 large towns. There's this business about the calcium concentration in the drinking water, but that's not particularly of interest in this problem. I think in this problem, what's of interest is the geographical region from where the observation is actually drawn, north or south of Derby. Now, what's certainly true about this is if you think about the sort of independence condition, initially it feels like, the regions are separated by some kind of line of demarcation. So you shouldn't think that knowing anything about the north or the south or the region north of Derby or the south of Derby should have any influence on your point of view about the other region's characteristics. You should feel like that's independent, at least that's what's suggested. I think it's a little trickier than that, to be honest. As long as there's no restriction in the ability to move around where you want to go, people can move around, I guess is what I'm saying. You can still study differing mortality rates. But if people move around a lot, that might confound stuff a little bit. So there could be some objections to this type of thing we're going to do here. We're trying to compare mean mortality in the two regions by looking at a sample of 34 towns from the north versus a sample of 27 towns from the south. There's also a question about what constitutes a large town. What's the definition of that? Do we think that, some small sample size, some relatively small sample size do we think that there really are hundreds of large towns in these two regions from which to draw a random sample? In fact, based on the description here, we don't even know that the towns were randomly selected. Possibly they were, but we would have to go back to the study. So there are a lot of questions in this problem about whether or not the techniques really even apply. We'll table those for the moment, and then try to use the techniques that we've learned so far, realizing that we're talking about trying to estimate something about the mean death rate. So let's write down some symbols and define them at least. We'll let mu sub n represent the mean death rate for all large towns in the north that are north of Derby, and let mu sub s represent something similar, the mean death rate for all large towns in the south. So the problem is evidently asking us to infer something about mu sub n minus mu sub s. Now, if you look at what might be an appropriate statistical hypothesis in this case, you know, there may be many, but if you look at it for a minute, it seems like in the north, their mean is far, far higher. It's quite a bit higher. So this is saying that the mean death rate in the north is about 1,632 deaths per 100,000. And in the south, it's 1,388, 1,389 for males in the south. So this does seem different. You know, it differs by maybe about 250, at least the average does. So, you know, because of this fact, you would wonder what you might test if you're a researcher here. So a statistical hypothesis, you know, a reasonable null hypothesis would be that there is no difference, which is, you know, maybe we don't have supporting evidence. Maybe we don't have evidence against that, I guess. The alternative might be, you know, you could formulate various different alternatives, but I think my favorite would be something like this, because you know, that's moderately consistent with what the samples would lead you to believe. Before I move on, does anyone have any questions about that? Notice I've suggested a one-sided test here. You could always perform a two-sided test to test for differences, but you know, let's try the other one right now. So let's see. We'll try to formulate the statistical hypotheses in this way. You know, what do we really see? So we can use StatCrunch to do this pretty quickly, and that's actually what we should probably do, because it is not so clear how to come up with the degrees of freedom that we're going to use in this case. So to use StatCrunch, and you know, in that way, go to we don't need that, but go to Stat, T-Statistics, to Sample with Summary, and a screen like this will be brought up. So for us, sample one will be the sample that's drawn from the north. So let's see what that would look like. So from the north, the mean is 1631.59. So we can enter that. The sample standard deviation from the north, is it's about 138.47. And the sample size from the north is 34, if memory serves. So the sample mean from the south is 1388.85. The sample standard deviation from the south is 151.114. And the sample size there is 27. I'm looking at a one-sided test, so I'll probably look at something like that. I'll choose that inequality as my alternative. I'm not really indicating much about the level of significance, but I hit compute, and what do I wind up with? So the sample difference is 242. We already knew that, and the standard error is about 37. So what this amounts to saying is that, you know, the difference in means is about like 6.46 more than zero. Standard error is more than zero, so it's quite a bit different than you would expect. You have a very low p-value. So when you run the statistical test, we find that the test statistic is about equal to 6. With the resulting p-value of less than 0.0001. So, you know, what is that p-value really saying? The probability of obtaining a test statistic, a realization of the test statistic this extreme, at least this extreme, is quite small. And this represents, so it's quite small, because I should add under, well, let me just erase all of that. under the null hypothesis, if the null is true. So we have evidence against the null. Whether or not you choose to reject the null, of course, depends on the level of significance that you would happen to choose in advance, but that p-value is lower than any reasonable level of significance. So in this particular case, I think it's fairly reasonable to reject the null. So if you go back to the problem, there's this additional question about what do you think the effect of the outlier would be? I kind of want to return to the image. So when you go back to the box plots that you see here, these box plots correspond to this particular problem. They are pretty symmetric. So you feel like, at least from that point of view, using the technique, at least at that level, the techniques aren't really in jeopardy. The samples look symmetric and unimodal. But with this guy right here, there's this guy up here that's the outlier. So the effect of an outlier in the north would basically be to bring that mean up. And so you would wonder a little bit about that outlier. And if you were to run the statistical test without the outlier, what would happen? That might actually be prudent, because that outlier, if you have a count of 34, may make the difference of means bigger than it should be, so to speak, without the outlier. So if you ignore the outlier, the outlying town, you may actually not find, you'd have to check, but you may actually not find, a significant difference between means. You probably will, though, because again, look at the box plots. I guess even without that, this guy's situated quite a bit above this guy. It's a possibility worth checking. We can always go back and look at the data set because I think it refers to a problem, but we probably won't do that. So at least for today, I think that's probably where I will end. If you have any questions, I'll hang around for another couple of minutes. But I feel like the discussion about measuring differences between between independent groups is now concluded. You want to make sure and finish the homework and look at the written assignment to make sure you think that. But I feel like at least that's enough for right now. Next week, we'll get into paired differences. Paired differences is a violation of the independence of groups condition, but it's a particular violation that's worth discussing. So that's chapter 21. If you've already done everything for next week, it's worthwhile going in and looking at chapter 21. And I think that's about it for today. So have a good afternoon.
Thank you.
Thank you. Thank you.